So we're going to talk about current mode, torque or force, in a possible runaway condition. If you don't control the velocity or position, you just command torque or force or current. You're going to get acceleration of mass or acceleration of inertia up to some point, and without any controls, it's kind of like the crash test dummy. So bad things can happen. So the idea then is to have some measure of protection for a speed limit. If you apply a torque or a current, and in this example, the current was applied at 10 amps. And you can see the actual motor velocity starts at 0 and starts to accelerate. This would be a large inertia, and we apply 10 amps and get torque and accelerate the inertia. You can see predictably that it would have continued to accelerate up to some speed based on some limit, and the limit being the motor's back EMF and the power supply voltage. So yeah, there's some inherent limits, but some motors can't handle 10,000 RPM or faster. The magnets might fling off. So you have to be careful, and maybe it's a good idea to limit the speed. Also, when you're going fast, you generate a lot of back EMF. And if you want to stop quickly and short the motor wires or something, you may have a lot of voltage and then current. So it's a measure of protection here. So what we've done in the new firmware 4.84 is we've allowed the velocity limit to be used to limit the speed even when you're in a current mode. So that's a cool feature. And you can see here that the velocity went up, but it hit the actual velocity limited at 4,000 RPM because that's what we programmed it to. And that's the parameter for the limited velocity also in the graph here. And so when you limit the speed, your current will fall back, of course. But so the important thing for this is, besides tuning the current loop for current mode or torque mode or force mode, you also have to tune the velocity loop if you're going to use it to set a limit, even in a current mode. There's a velocity limit parameter 0x3a, which is on the V-loop screen, which you don't see in a current mode, but you can enable that screen and set the parameter, or you can write to it, and that's in units of 0.1 counts per second, or counts per second. And then there's a new parameter 0x154, the servo loop configuration, or a new bit, the bit 6. When we turn it on, it will use the velocity limit to not allow the speed to increase past some limit. So we'll take a look at a typical current mode configuration. This is a program current. This could be your master that's sending out CST commands, cyclic synchronous torque, or maybe a controller that has a plus or minus 10. And again, if you don't get the feedback, you could get this runaway condition, and the motor ramps up based on the torque or current you apply. And so it's kind of a safety parameter or a safety precaution, not certified safety, but sometimes for safety you need double redundancy. So there are things we can do to protect equipment. There's other things you can do to protect life. So that's, are you going to die, and how likely is it you're going to die? So maybe your system needs certified safety and not just some safe parameters. So anyways, in a current mode here, I've got a motor, I've got 24 volt back EMF, and I'm going to enable the drive. It's commanding 0 current, and I'm going to apply some current. It's a very low current, hardly get up to very much speed, but I'm kind of getting close to the voltage limit. Let's give it a full half an amp. And so, yeah, so you can see the warning here. voltage limit warning. So I can't go any faster in this system because I only got 24 volts. But if I had 240 volts, I could go 10 times faster, 10,000 RPM, and fling the magnets off. So what we're going to do then is take a look at the current loop, and you can see the command and an actual current. The gains of the current loop have been tuned, so we have good current loop response. That's great. But if I do half an amp again, and I'm going to do a lower frequency, make the trace time something longer. Let's do 1 hertz. So I'm going to accelerate up when I apply current, and I'm going to reach the speed. You can see in this that I'm limited, voltage limited. I trace that parameter pretty quickly, so the current goes up to the command, and then I hit the voltage limit and it folds back. That's just Ohm's law. You need voltage to produce current, there's some resistance in the winding. So velocity, actual motor velocity, we can also trace that, and you can see that during this time we're accelerating the inertia, and then it hits a limit. The limit here is about 1,000 RPM because the motor has back EMF, and there's some winding resistance. So all the voltage goes to producing as much speed as possible, and then the current folds back. That's just what happens. So to set the velocity limit to something lower, we can go to the basic setup, put it in a velocity mode, and still software programmed. This gives me access to the V-loop screen where I can set a velocity limit. I type in 500 RPM, and I look at ASCII command line I get from RAM 0x154. It's 0. S for set, 0x RAM. RAM and flash, I'm just going to do RAM. You want to save the value, you got to write it to flash. But bit 6 is the decimal 64. I'll use the programming calculator. Bit 4, 5, I click on bit 6, I get a decimal 64. I could do hex, 0x40 or x40. But we'll just set this. So now in RAM is that speed limit, and I'm gonna leave it in velocity mode here, but we can go back. The function generator uses the current mode, but so we can see now the actual motor velocity will be limited to 500 RPM. And the tuning of the velocity loop is important. That's, when you're switching to velocity mode, you'll see a little ring as the loop stabilizes. So there are gains in the velocity loop which can be applied. I can, lower the frequency for a large inertia, and I can cut the gains down to try to get a better hold of that without too much ringing. So you'll see a slightly different, longer bounce and maybe less of a bounce here. And yeah, so it's sort of critically damped as we slide into position. So lower gains, doesn't cause the loop to ring when you disturb it. You're suddenly changing from current into velocity limit, and the loop gets disturbed. I don't believe these parameters have anything to do with it. As the note said, you can see the acceleration is purely limited by the current, not by any velocity loop parameters. So this is the only parameter which takes effect. Yeah, if I had a lot of current, I couldn't go that fast, but I am going that fast, so low current. And so you can see now the lower parameter. Yeah, you get a little voltage limit happening when you're hitting it with the command current, but the velocity can be programmed using the velocity parameter tab. And then just to show how that works, even in a current mode, take it out of velocity mode, keep it in a current mode, Okay, and just from the control panel, I can enable, I'm going to hit it with a 1 amp, large current. So it accelerated quickly to the velocity, the program velocity limit. And that parameter was 0x3a, just to show you that ASCII is a little bit different than user unit. So get from RAM 0x3a. This is based on your counts per rev. I've got 131,072 counts per rev. I'm going about 2 revs a second, so double, more than double, and then move the decimal point over. So big number here for, this equals 250 RPM, the same value that we programmed on the V-loop screen. Okay, I think that's it. Potential ideas for the future. Maybe there's a way to limit the position. Haven't figured out how to do that yet, but maybe someone will let me know. Okay, thanks for watching.